Second pre-question video. Those are the questions I'm going to do. I'll start with 2020 question 9. And I was asked specifically for parts of these questions. So the first one had to do with the guitar string. The guitar string is plucked. There's a magnet in the vicinity, so you have a changing magnetic field cutting a coil and induces an EMF in that coil. The coil is the string. The string goes back and forward relative to the magnet, and we get an alternating current produced. Now, when you pluck the string initially, the amplitude of the string is quite large, so its speed passing the magnet is quite large as well. So that means there's a large EMF induced. Over time, the amplitude decreases, and if the amplitude decreases, the string, which is the coil, actually moves slower on average past the bar magnet, so the EMF induced is smaller. And that's why we have the shape of the graph that we have there. So it's definitely a sine type of graph. It's definitely that wave shape, but you can see the amplitude decreases, and it does so because over time the speed of the guitar string as it passes the magnet is less, so according to Faraday's law the induced EMF is less. Now, the oscillation decreases quicker in the case of a guitar string also than if it was left to oscillate without the presence of a magnet in the vicinity, and that's because of Lenz's law introducing a back EMF into the system. So that's just a bit of background information on it. I think you were just only asked for the graph, so there it is. Okay, the next part then was how you'd calculate the speed of the wave on a stretched string. So I've derived it here, and you'll see it again, I think, in the next question. It popped up quite frequently in 2020, as in twice, but it's there nonetheless. So if we start there with the diagram on the left, when we're talking about the fundamental frequency of a stretched string, that skipping rope shape there is half a wavelength. So if you cross multiply, you get 2 times that length is equal to 1 wavelength. Now we bank that knowledge, and then we go to the formula F is 1 over 2L root T over mu, which relates to frequency, length, tension, and mass per unit length for a stretched string. And what I do there in the second step is I cross multiply by the 2L, and we've banked the fact that the 2L is equal to lambda. So you now have F lambda is equal to root T over mu, but sure, F lambda is equal to C. So to get the speed of the wave on that stretched string, you can get the square root of the tension divided by the mass per unit length. That's something to remember. I did cover it when we did this section, but it seems to be lost amongst a few of you, so you might just remember, in that particular case, just remember the derivation. Okay. 2019 question 4, I was asked to recap. This is the semiconductor V versus I experiment. The circuit diagram there is on the left. I've omitted the labels. Please do not omit your labels on the diagram. You should have labelled the variable power supply, the rheostat, the diode, the milliammeter and the millivoltmeter. And I specifically have milliammeter and millivoltmeter there because the table has units of milliamps and millivolts in them. Going to the top right hand corner, your graph then should also have millivolts and milliamps as the unit, and your line or curve or fit will be more or less horizontal to start with, and then it shoots up sharply towards the top right hand corner. I've got an arrow as well telling you where you need to look to find the junction voltage. So when that line or curve or shape goes from a straight line over and starts to pick up, that immediate point there when it starts to shoot up, that's the junction voltage. And you just read that value for the junction voltage off the x-intercept, or the position of the x-axis. Okay, the remainder of the question then. How do you know you've exceeded the junction voltage? A current flows readily. Does it obey Ohm's law? No, it does not, because it's not a straight line graph through the origin, or because you can see from the graph that V is not proportional to I, which is demonstrated by the straight line graph through the origin. And then the last part, it says name 2 other changes to make to the circuit. So the original circuit is on the left hand side and the rearranged circuit is on the bottom right hand side. And there are a few things that happen. Number 1, the milliammeter needs to be changed to a microammeter because the currents are much smaller in the circuit. The diode obviously is flipped around, and also the milliammeter is placed in series with the reverse bias diode, and the voltmeters are connected across both of the 2 of those. All right, next question. 2018 question 7, I was asked just to recap quickly about sound intensity. So intensity in general is the effect that you experience as energy dissipates through space if you're at a particular distance from the epicenter of that energy explosion. A lot of big words there. Basically, think ripple in the pond, and then the ripple spreads out, and if a duck is a distance from the origin of the ripple, that duck is going to experience less of the overall energy than if they were closer to the ripple. So, sound intensity is power over area. The sound intensity in this case doesn't spread out over 2D like a ripple in water. It spreads out like an ever-increasing sphere. So the energy is dissipated or spread throughout the shell in 3D. So we're talking surface area of a sphere in that case. So A is equal to 4 pi r squared. That means then that the sound intensity is proportional to 1 over r squared. So if we double the r, the sound intensity decreases by a factor of 4. Now we know as well from the syllabus that if the sound intensity changes by 2, if it doubles by 2, the sound intensity level increases by 3 decibels. If the sound intensity decreases or divides by 2, the sound intensity level subtracts by 3 decibels. For us, R was doubled, so that sound intensity decreased by a multiple of 4, in which case the sound intensity decreases by 6. And I think I have not got that in there. So it's minus 6 decibels is the answer for the last part. And the last one I'll do in this video is 2017 question 2. And I mentioned this sort of thing already. So there's your graph, F against root T. Don't forget, if it's the square root of tension, the units are square root of newtons. So I rearrange my formula to get the F, the Y thing on its own, and I should have the root T on its own there. There's obviously a mistake there. I'll come back to that in the next video if you don't mind.